background about me. So I think it's important. So I am from originally from India, but I living in Finland for the last 12 years. So I have done my master's and PhD in Finland from Aalto University. I've been working with ABB almost for now 7 years. And along with that, I have my own startup company here, which works with EV charging solutions. I am the CEO and co-founder of that company. But today I will be speaking mostly on electrical machines. So basically, uh, idea was this that we have a lot of young researchers and students here in this call, and idea was this that I'm going to speak a little bit about that how we do industrial research and how from academic world how we come and then how we solve real life problems. So I think that it can be very much motivating for a lot of our PhDs and postdocs. And I'm also coming from an academic background. I totally understand the, let's say, challenges of academic world and so on and so forth. But let's try to go through these presentations now, and let's see that what the things that we do, what type of collaborations we do with the universities and so on. So what is my job in ABB? For example, I am kind of the person who develop and manage our digital services and softwares on electric and machine related things. So we have a digital platform for our division in ABB. And then a lot of my work actually comes for collaborations between different teams inside ABB, for example, Germany, and then Sweden, USA, India, and of course, Finland. So basically collaboration is kind of like a very key thing for me. So we have to collaborate on different projects on industrial AI, condition monitorings with drives. And then I also do a lot of consultations for ABB's different research projects. So the main thing that our team does is that we handle our in-house software in ABB that's called Adept. So you know that there are a lot of commercial software available, right? Let's say Maxwell, and then, for example, Opera, Flux2D, Console. So Adept is kind of like an umbrella under which we have our in-house softwares and also commercial software. So it is like a bigger umbrella, because if you think about like a big company like ABB, we have a very big portfolio. So it has to be very much organized how things are done and so on. So one very important idea for whenever you think about any big organization or any complex system, when you have multiple researchers, multiple people working in different field and in different divisions, in different geographical locations, that how do you collaborate? And I think the modern way of collaborations is basically microservices. That means that, for example, some of you, let's say person A develops some model and person B wants to use that model, then it is very bad. For example, if person A need to zip a file, send it to person B, and so on and so forth, because you know that then the software is never updated and so on and so forth. But idea is this that everybody can be the owner of their own services and they can host it in the cloud, for example. And anybody who needs to know those things, they can basically just call those API. I don't know how many of you are familiar with the word API. It is basically kind of like let's say okay, I think the abbreviation is something like application programmable interface or something like that, but mainly it's basically an URL link and with some sort of a token, let's say like a JSON file that you give to get and receive information. For example, this picture that you are seeing, it is basically in a web page, that this kind of a flux density plot. So not any software, but through HTML page, we can do that kind of thing. So everything is can happen on the browser. You do not need any desktop GUI software actually in modern day. I think there are few commercial software who are now trying to give you similar experiences, but I would say that we are kind of like very advanced in that part, that everything, nothing is on the desktop, but everything is on the cloud. Then one of my very first work when I came from the fresh PhD student to ABB was this, that how we do system level simulations with Drive. So I think that many of you know that in modern day, whenever we talk about system efficiency, or let's say efficiency, it is not about only individual component. I think we have a VinFast speaker after me, and he can maybe speak more on that. If you think about, for example, even an electric car, for example, every component efficiency matters and add up in the end. But how do you basically model that kind of a system level efficiency or system level behavior? For example, if you think that about a drive, when a drive is connected to a machine, then there are a lot of things that happen which does not happen when you connected it with a direct online. For example, drive has a very ugly voltage waveform. It can create vibrations, it can create noise. So how do you model them? If you just model it with a sinusoidal supply, then that's very bad. If you just model it even with a PWM supply, then it is still not very realistic. The ideal situation is this, that your voltage or your drive software should directly communicate with your finite element software. So basically it should give you, let's say, voltage waveform, and the current that you are solving in your finite element solver should again get back to the control mechanism of your drive software. So I worked on this kind of topic during my PhD. And then when I came to, for example, ABB, that is first thing that I did was this, to integrate our drive software with our machine software. And it is a closed loop integrations. So that basically means that the voltage waveform coming from the drive, finite element software solve it, the current that it is solved, the torque, angular velocity, rotor position, everything that you solve from the finite element goes back to the drive again. So it's a closed loop simulations. The benefit is this, that your iron loss estimations is much more accurate now. Your understanding of vibration and noise is much more accurate now. And then to scope to optimize the whole drive system becomes much easier. For example, you can optimize the whole system level simulations using, let's say, you can optimize the switching frequency of the drive to know that what is the best possible scenario for a system level behavior and so on. But sometimes to make this kind of software coupling strongly can be very challenging. So for example, for some other drives, we do not have that. It was very challenging for us to do that. And to do so in those kind of scenario, what we do is that we call it weak coupling, where we basically solve the voltage waveform using an analytical model. And with that, we basically store the voltage waveform, and then like an open loop, we solve the finite element. And I think that most of the cases in commercial software, majority of the people are doing like that. So that when it is very complex to make a strong coupling, then they do this kind of a weak coupling, that they just store the voltage waveform using an analytical model from their MATLAB Simulink, for example. And then that waveform, then they give it like more of an open loop model. So this kind of work requires really a very strong collaborations and cooperations, because, for example, I am not the person who make the drive software. I'm not the person who make the finite element software. But then I have to keep and asking people and develop that kind of an interface. And that is required kind of like very collaborations and cooperation. That is very important. In academic world, you are kind of like quite tied with very easy softwares. Let's say MATLAB, which is a very easy software to learn and good for, let's say, researchers. But for example, whenever we do work in the industry, it is never or very seldom with MATLAB, because it cannot be, let's say, easily distributable, and it is expensive also. So normally it is worked with, let's say, C++ is a great tool when we work with a lot of this kind of a software development. Then, for example, for any cloud-related development or web-related development like API and microservices, we always use Go language, which is a language programming language developed by Google. The reason I'm telling this kind of small tips, I think that can be helpful for you when you proceed with your career and then want to go into the industry. Then you know that what are the gaps that you have, and that how what you need to then overcome to get to get more industry friendly with your job. And always, for example, our philosophy is that we look for the low hanging fruit. So lot of times that's the difference with the academic and industrial world, is this, that in academic world, sometimes we are lost with a very high, let's say, aspirations, and that's good. That's how it need to be. But in industrial world, we always look for what is a low hanging fruit, so that we can easily get some result in a quick iterations. So that's a very philosophical differences, I would say. And then one very important thing to remember is this, that whenever you think about finite element software, it is more of a comparative measurement and not what absolute values. So that is another thing to remember, very important. That do not think that, okay, if it is 20 kilowatt, you need to match a 20 kilowatt. Nothing like that. It is always that how much better the design is in a comparative scenario. That's how you use finite element. Then, for example, as I said that our main software is Adept, but then also we collaborate with third-party software. And in a company like ABB, which is a very big organization, for example, it is impossible to make individually Maxwell model of our thousands of machines. So we needed some sort of an interface again that we can integrate Ansys Maxwell with Adept so that people can open our software Adept and which has all the machine informations and click one button and then automatically this whole Maxwell model is developed from our database. So that is kind of require a collaboration. So we had collaborated with Maxwell. We had a 2 or 3 years of project with them, and then we developed something. So I can very quickly show you a video maybe. So it's written on the top. Behind the hood, there are more than 8,000 lines of code developed in Python, which does all the trick. But here it is that you just decide what machines you want. You just click some buttons and pretty much that's it. So then Maxwell will automatically open and it will collect all the informations. This is geometrical informations, operational informations that you have in your machine. It will collect those informations and then it will just develop the model for you. So this kind of integrations we have done with Maxwell. And I think we are one of the biggest user of Maxwell software also along with along with our in-house software. But as you see that here, when user click that one button, all those model developments are done exactly like how it is done. And for example, it is benefit of this is that a lot of our geometries are very much ABB specific. So it is not possible to have those in Maxwell. So they do not have those kind of a template or anything. But here the idea is this that whenever user click it, they get all the necessary information. Let's say torque, current, loss, flux densities, and those kind of plots and everything, and so on and so forth. So these are like very important to know that how we can make things faster, because if you can save time for one of model development by 1 hour. So if somebody need to develop a model like this by themselves, it can take them, let's say, a couple of hours. But it now with this kind of interface integrations, in 10 seconds, they can develop a model. So if you think about ABB, which like have so many engineers and so many machines we need to develop, it saves a huge amount of work time. And that is very, very important, that how you save time for your development. Okay, and now I think that with Maxwell, we have done some interesting work that we did a thorough analysis that how 2D versus 3D simulations are compared. I know that a lot of people like in the academic world also, for example, we have a huge fascination about 3D simulations, and it is rightly so because a lot of electrical machine phenomenon are 3D. So it is good to know those informations in 3D and verify how close our 2D approximations works through. So we did kind of like a humongous amount of, let's say, comparison of 2D and 3D simulations. We use our server. We have our own internal servers where we have a huge amount of computational resources, and we did them. So we make a 2D model and then with 3D model, and our goal was to see that how much accuracy we are getting with and how much computational time we have to lose. So if you can see that with a 2D model, for example, we can simulate something within 5 minutes with this kind of a mesh. And then the same thing when we use in our server, and we have been using 40 cores. It took around 61 hours for us. So almost like say 2.5 days. And idea was to check how this torque looks like, for example, and then how other features looks like. Then we did similar analysis with induction machines, for example, same thing that 2D and 3D. And for us, it is very easy to do, as I said, because we have this kind of an interface, like I showed you previously. So we can just click one button that made 3D model. So all these things, this model build up, they are happening automatically. And that is the benefit that we can do this kind of an analysis very, very easy, very, very fast, because those things are very automatic, all these model generations. And then we compared the 2D and 3D rotor when it is queued and so on and so forth. And you can clearly see that the 3D behavior is, of course, better than that 2D approximations, some current waveform and so on. Then when it comes to, for example, noise analysis and vibration analysis, you know that it is important to know what are the electromagnetic forces, especially there are a lot of models, for example, but one of the model is that you compute the forces in this kind of region in tooth and in the air gap. So this kind of automatic meshing and automatic computation is also have been done automated way, so that you just click one button that I want to compute the forces, and then automatically there will be 4 layer of things will be created. It will be mesh. This kind of arc will be created and force computations will be done, and everything happens with one click. So R&D engineers, they do not need to do those things by themselves every time. So we save a huge amount of time with this kind of software automations. Then, for example, we have this kind of segmentations, like magnet segmentations, that how you segment the magnet so that you can get less losses in the magnet. I mean, probably most of you know that when it is 50 hertz, perhaps it doesn't matter so much, but whenever you go a little bit higher frequencies, then eddy current is a concern. So how you model that kind of a problem in 3D, because as you saw in previously that it can take a huge amount of time. And in this case, you need the mesh very dense if you want to model the skin effect, isn't it? So how you model that? So we have taken, and this is not my inventions. This is coming from our ANSYS Maxwell colleagues who have helped us to do this kind of a simulation. So they help us to automate this. So now, for example, with one click, again, we can have this kind of a geometry created, that it will be automatically dense mesh will be created, and we solve, for example, here the skin effect. And then we basically apply some sort of a boundary conditions here, which basically means that there is some sort of an insulations that is coming from the segmentations, and then we just multiply them. So basically, that's what I have written. Only one segment eddy effect activated, thus because it prevents short circuit between magnets and act as an insulation mathematically. So if you give a boundary condition, then that means that the current is not flowing from one segment to the another. So there's a very smart way to model magnet 3D segmentations, for example, with Maxwell. And then you can see some results here, how the losses are. Okay, then in the beginning, I said that I am also very much collaborating with industrial AI. Actually, for the last 2 years or 3 years, I have been quite active with a lot of industrial AI related projects. And that's how I also know Trung, I think. So we do collaborations with our different research institutions in Finland. We do collaborations with the university, and I think it's a win-win situations when we do collaborations with institutions and universities, because then together we can create very nice value out of the work. This is one collaboration that we did with a Finnish research institute called VTT. And the goal was this, that when you think about induction machines, whenever it is connected with a grid, then there is a huge transient, right? That's the whole starting behavior of induction machine. It is a quite transient behavior. So we wanted to model that with artificial neural network. And then we thought that this can be used as a digital twin, for example, of induction machine behavior. So here the complexity lies that how you can model a transient behavior in a time series. So, like you need to take, so how this is beneficial is this, that you need to take the the input of your change of your rotor speed every 10 seconds. That's how we take it as a back propagations, and then we model this in using this kind of artificial neural network. Then also one of the important thing that always come to our desk is this, that how you model the losses of electrical machine using machine learning. Because if you think about electrical machines, there are, let's say, 3 key components that influence the losses. One is where the speed is, or what is the speed of your machine, what is the torque of the machine, and at which switching frequency of the drive you are operating your machine. So there are like 3 components that mostly influence the losses. And our goal was that can we create a machine learning, or let's say AI-based digital twin of the electrical machine that can take those 3 inputs and can quickly predict the losses accurately. And then we benchmark different machine learning model. We use neural network, we use light gradient based methods, we use lookup table based methods. Okay. And at least what we have observed is that very simple lookup table based method is not good. Whenever you have more and more dimension to interpolate, that's not good. Then going too complex neural network is also not super good for us. But what we found good is that this kind of light gradient based regressions models, they are very good, giving very good results to us. So this kind of a quick model that can predict the losses can be very beneficial when you think that in the real time you need to model the temperature distribution of the machines and so on and so forth. And these are like all public information. So paper has been written. So if you just Google and search in IEEE, you can find all these informations actually in detail. Then one of the work that we have been doing recently also with Aalto University was this, that how we can design an electrical machine using reinforcement learning. I mean, if you think about us, that we engineers, let's say, if we are being asked to design a machine, how we think? We normally think that, okay, I have a machine, I have to design. Let me try to find some machine which are very close enough with this machine. Maybe then I try to adjust some coil, turn, maybe I increase the length a little bit, maybe I do some height adjustment of the slot. And that is how we, in the beginning, we do the initial dimensioning, right, of the machine. Of course, afterwards, then we do some more advanced optimization, let's say particle swarm optimization or any genetic optimization, but those comes in the second stage. But in the beginning, when you need to dimension a machine, we do dimensioning like that. Let's say with our engineering approach or our engineering knowledge that we use, that okay, you design this little bit, you increase that little bit, so on and so forth. But we decided that can this engineering behavior, can this be mimicked? I mean, if we think, for example, you will listen that this kind of a news comes quite often that AI has defeated a chess player. AI has defeated another chess player with some games and like that. What happened is this, that in theory, our machine learning algorithm, and this is called this kind of unsupervised machine learning algorithm, and reinforcement learning is one of the, let's say, branch of unsupervised machine learning algorithm. Sorry, I go back. When we talk about machine learning in this kind of scenario, it is a supervised learning, because you have a clear understanding that what are the operating point, what are the losses, every data is there, and you are just modeling. So it is a supervised learning. But in case of reinforcement learning, it is an unsupervised learning. So this is the fundamental difference, is this, that you do not tell the agent that what are the outputs. You tell the agent that what is the behavior of the system. That means that, for example, you play with the AI, let's say a chess game, and you play it many times. And if the game is played good in a good way, for example, if the AI make a good decision, and then you give them a reward. If the AI make a bad move towards the goal, you give them a penalty. So you basically let the AI to play the electrical machine game millions of times you let them play and see that if it can reach the final goal or not. If you have a, let's say, base machine, let's say you took a machine from the vault, which is, let's say, 50 kilowatt, and then you give a task to the AI that, hey, I have a basic design of a 50 kilowatt machine. Then you make me a 60 kilowatt machine for this and these conditions. And you make them to play this kind of game more and more and more. And when it play million of time, these games, it knows exactly the policy. Please remember this word, policy. It remembered this policy of the game, that okay, if I play this way, I get reward because I can achieve my target. If I play this way, I do not get a reward, I get a penalty, and I lose the game. So this is the idea of reinforcement learning, where we investigated with Aalto University, and we are now submitted a paper also. The idea is this, that how we basically design a machine using reinforcement learning. So for example, if this is the starting point of a machine, and if this is the goal, how the algorithm automatically can make these decisions to get into this kind of a final design. For example, if you ask any experienced electrical engineer, he can also do the same thing, maybe with the less iterations. Like he can maybe tell it already that my second guess will be this and my third guess will be this. But we wanted to check that how the algorithm, without having an electrical machine knowledge, can it learn the policy of the game. So we give different cases. We tried with 1400 kilowatt, 360 kilowatt, 1450 kilowatt. And in each point, blue point is the starting machine. So this is the base machine. And then from there, we tell them, hey, can you design another machine? And then it try to reach the design. And it seems that it managed, in majority of the cases, it managed when we train them well. One of the biggest challenges is that how you define the reward. So what type of behavior or reward functions need to be developed that it knows that what is a good design and what is a bad design. And those are the challenges that we wanted to address in this kind of work. Then we also work quite actively with the bearing health analysis using machine learning. And this is also another collaboration that we do with Aalto University. So as you know that bearing fault is kind of like, let's say 50% of the industrial machine fault comes from bearing fault. And there can be many ways this bearing have fault. I mean, if this outer ring is destroyed, then there can be one type of fault. If the inner ring is destroyed, there can be another kind of fault. And there are so many other ways the fault can be developed. So we took this kind of let's say modeling that where we have a huge amount of simulations we've done, and then we wanted to model that how the bearing fault can be modeled with this kind of a machine learning. So we have this kind of an electromechanics model for the bearing, which is basically a lump parameter based bearing model. And then when we collect the data, so you see that in the real life, we use this kind of a smart sensor. You can Google about ABB smart sensor. It's a device that can collect different kind of data from the machine. It can collect, for example, flux, voltage. It can collect vibrations. It can collect temperature and all those signals it collects. And once it collects all this data, it can send it to the cloud. Okay. And then the goal is that we can analyze this data to see that we do this kind of a frequency and time domain analysis. Then we have our model that basically do this kind of a AI based fault diagnosis based on this kind of a data crunching. And then the goal is this, that how we can have this kind of a model to predict that, okay, if the machine is having some bearing problem or not. If there is some sort of a bearing problem, we can see that signals in our cloud dashboard. Then we can already tell our service engineer that, hey, maybe you need to visit this factory and tell the manager that the machine needs some sort of an inspections. Because when you do this kind of a predictive maintenance, then you save a huge downtime for the machine. And if machines are normally used in a factory where there are huge processes, they are dependent. So if one machine got breakdown, the processes are stopped, and then there's a huge loss in that factory. So when you do this kind of a predictive based maintenance, and you can tell that, hey, you need you reduce the downtime, you reduce a huge amount of money you save for the factory. So it's not only the electrical machine cost, it's the whole process cost that you save. Then another work that we are doing right now is that anomaly detections of induction machines. Something very similar, but here the work is a little bit the approach is different in that way that we wanted to use this kind of an autoencoder based system. That basically means that that we wanted to know that what are the healthy data and then what are the faulty data. And then we just wanted to segregate the healthy and the faulty data with this kind of an autoencoders. But as you know that in any industrial AI work, the biggest challenge is to get the data. We cannot have faulty machine data in a measurement. So how do we solve this problem? The problem that we solve is with simulating those machines with the faulty conditions. But hey, there is another problem there. Your simulation world and your measurement world, they're different. So your simulated data will look very different than your measured data, right? So how you basically solve this problem? And that is exactly where these data augmentations come in. So when you know your measurement data and when you know your simulated data, you can basically understand that what are the differences of the simulated data with the measured data. And then you can augment the noises and then the uncertainties that comes in the measured data inside your simulated data, so that your simulated data become more close to the reality. That is what we call data augmentations, that you basically calculate the data from simulations and measure, and then you basically use some sort of a model that assimilate the data and then makes this simulated data very close or similar looking like this measurement data. The reason of this was this, that we wanted to have a huge amount of data to create the machine learning model. And for that, we are using also our simulation software and our measurement together to create this kind of data for the machine learning model. So this is pretty much it from my side. I think I a little bit go overboard today, but anyhow, the four conclusion I will give you as a thought, all the young researchers that we have today, that in university, research is the priority, but in the industry, development is the priority. And then in university, for example, we are kind of like a lone warrior. We are like doing our own battle by ourselves. But in industry, collaborations and communication is the key to get your work done, because you will be working with multiple stakeholders, and how you communicate in which language and how you basically get the collaborations, it is extremely important. Then another thing is this, that in academic world, we normally reinvent the wheel a lot of time. But in industry, your goal is not to reinvent the wheel. So you have to use the work that has been done by your colleagues. You have to ask them, collaborate them, and then your goal is to basically bring a value out of the work. And customer success story, that's why depends not only on the innovations, but also on the implementations. So that's it from my side, guys. I hope you enjoyed this presentation.
Thank you, Victor. It's very nice, impressive presentation. But I would say there are quite many questions I want to raise, but I have to let the audience ask you some question first. Is there any question from audience, please?
Yes, it has speaking, and thank Victor. I found the chance to collaborate with your side. Many things I think is open for the ABB and VinFast. I'm very interested in the bearing health analysis with machine learning, because as you already addressed, the 80% of the issue happen now with the traction motor or on the market is related to the bearing, and how to predict it in earlier and have the appropriate action to the customer side is very important. So I really appreciate if we can have the contact after this discussion and looking for more detail about this.
Yes, and I will write my Kroong know my email address, so Kroong can be your contact person, and Kroong can send me the email, so we can definitely discuss. Not a problem. Yes.
Okay. Yeah.
Yeah, but
Thank
we
you.
can take it
Super happy to hear. I'm
in a
super
private.
happy to hear. I'm super happy to hear. Really, really. I mean, this is the goal, right? I mean, Victor, I also, my kid, 19 years old kid, also listening to you, and hope he feel inspired by you as well. But also, the goal here is to find a chance for collaborating. And Anh Hải, I think for the condition monitoring and so on and so forth, Professor Kang also from Norway, he also doing something with it. And Professor Kang and Victor also have strong connection. So I hope all of you guys will have something to work together in the future. So that's my wish. No question from my side, but I really appreciate and I'm so happy to hear. That's all from my side. Thanks.
I work for Bearings for about 10 years, from from offshore industry, different type bearing, bonds bearing, and abnormal detection and localized bearing faults. Apply AI that the strong part of my group for many years. So I think we should open for collaboration on this topic. Anyway, in our group we even have open data for research community to get the data from our group. We had the test bed to test the from the run to failure in different speed profile, and then people can just download data from us to develop any sort of apply AI or apply signal processing to detect the bearing fault. In several slides, we talk about if anyone study about the bearing fault, they should join the, let's say, the course from Mobius from US, and they should understand the several stages of the bearing faults and what stage we are talking about now. We will talk in probably separate forum anyway. Okay, so We had a first question here from Wu Kan from Kerry in Korea. Kan, please.
Thank you, Dr. Khan. And hello, Victor. Hello, Dr. Victor. Nice to meet you again. And I think last time we met on ICM in Torino. So
Yeah.
I just want to clarify what the system analysis of your work. So in the slide 3, maybe around slide 3. So I just wonder, when you do the system analysis with the driver and the electromagnetic analysis, usually you use a lookup table version or some or other model to just predict the electromagnetic performance of the motor when you do the system analysis. And if you do the kind of analytical equation or the lookup table model, usually when I work with some application like traction application, we want to consider some like AC copper loss analysis or iron loss, consider the effect from the PWM control technique. So how we have you if we want to using FEA with that system analysis, is it possible? I think the time step between the control in the system analysis and the time step of FEA analysis is too big difference, so it can make many trouble. So I just want to hear your opinion on the problem when do system analysis.
Yeah, so I will let's see how I can answer this. I'd be very careful how I choose my words because I do not want to tell confidential part. But let's say I can say it like this, that one problem with your lookup table approach is that it is constrained by how you are designing your lookup table. I mean, when you think about drives, and if you have a, let's say, different way you can operate a drive, right? If you have a sine filter, if you have a 2-level or 3-level inverter, if you have a switching frequency, this or that. So how many variability you're going to put to your lookup table? I mean, there is no end of that. So that is a problem with that kind of an approach. So that's why I believe that a closed loop system simulations is the best, where you have your drive software and your finite element software. They are both in the same. So your software, for your finite element software, for example, all it needs to know the voltage waveform, right? That's the only thing that it needs, the voltage waveform. And what your drives needs, it's only need to know the current as a feedback so that it can generate the correct voltage waveform. Of course, it needs the torque and angular position. I don't want to go so technical at this point, but so basically you have to understand that thing. So that is very important, that what each system needs. Now, the reason is this, that, for example, the challenge, I would say that what I have faced, that how you make the system stable. So because if you just do a coupling, let's you just put a finite element software and you just put a drive and you say that, okay, I want to have a closed loop simulation. I would say that in the beginning, you will say that your system is not stable. It is not converging. It is the torque is like bouncing like hell and so on the current. So that is the trick. That's the problem that we have solved internally, that how you make a stable system level simulation. So we have our tricks, our own IP, our own, let's say, approaches. But that is the thing that we have solved. But the idea is that to have it in a very, very, let's say that like a real life scenario, not like with a lookup table, because then you are far away from the reality already. So for example, if your drive team wants to have a new algorithm to try and test that, okay, I have a new algorithm and I would like to try and test that how it can reduce the noises, how you can do that. So you have to then do it directly in the system level. They can just try and that kind of simulations. So that is the trick, I would say, to go forwards, that you have to just design a closed loop simulations which is stable. So and that is that thing that you need to solve.
Thank you for the answer. Thank you so much.
It is clear for you, Khan?
Just can you say again?
It is clear for you. The explanation is clear for you.
Clear about the answer. Yes.
Yeah, because actually this I was in the same group with Victor before, so I have also do some sort of let's say copper model. It's very important to understand what you want to get from your finite element models, and if you simulate you want to take into account the impact from the drive, and then you have to know what's the drive type waveform the right could offer, let's say, the output of the inverters waveform in different control scenario, and what would be the signal you can get into your finite element model, and then you can calculate loss distribution and type loss based on that. That's my guess. Is that correct, Victor? Or you want to keep it secret? Okay, any more question from audience, please?
Maybe one question from me.
Yes, please.
I mean, not really technical things, but like, what is job opportunity in your group? Is it really like, is your team manpower fluctuate a lot and there is a opening position quite often? And if somebody want to apply for the job in your team, for example, can they contact you for like how to say, suggestion and so on and so forth, for reference as well?
Yeah, it is possible. They can contact me. Definitely, they can contact me. And normally, yeah, we have some positions opened every year. Normally, not so much in the job, but at least for the thesis, PhD thesis, master thesis, that kind of positions are every time open. And majority of the time, I am the person who is coordinating them. So fortunately or unfortunately, so I have to be responsible. So mainly, I am advising master thesis every year. Also, PhD advising is also part of my thing. And normally these days for me, research is mostly advising. Not I do not do much research by myself, but mostly through advisory only I contact them. But yes, but mostly these are done normally within the Finnish universities. That is one key thing because it's much easy for us for the bureaucracy purpose, and anyhow we have a lot of resources available in Finland. So normally whenever we recruit normally locally majority of the time.
Understood. Thank you. And I think same situation with my team in Germany. We have open position for student, master thesis, internship, and so on, even PhD thesis. But we prioritize student from Europe because of documentation work is a lower load for the human resource team. But thanks. I think many students here have electrical machine background. So I think it's good for you to know Victor as a reference point in case you want to go to Europe for internship or whatever you want. Thanks, Victor.
Thank you, and thank you, Trung, for giving this opportunity. I mean, I really enjoyed speaking about electrical machine after a very long time. I don't get that kind of opportunity much these days, but thank you. Yes.
Any more question from audience, please?
Yes, I have one more question. Can you tell me what are the applications you usually have? Do you do like standard machines or customized machines?
So let's say majority of the machines are industrial machines for us. So applications is basically, I mean, you can check the ABB portfolio on internet, but let's say mining and metals, and then for example, process industries, then for example, traction also we have a huge application. This just traction team is growing quite nicely. Traction, not like a car, but we have, let's say, big machines, then railways, that kind of places. Then we have even bigger machines for a different mining, very, very big motors or machines that goes. Then, for example, a company like we also sell generators. For example, companies like Wärtsilä, and they buy a lot of generators from us. So we have a huge product portfolio. We cater the low voltage, medium voltage, and high voltage segment, all sort of machines. And I think ABB is probably the number one in electrical machine portfolio and electrical machine company in the world right now. But you can check more on our website about the different applications.
Thank you. And the manufacturing, do you do it in-house or with different partners?
In-house and with partners, both. And we have different manufacturing divisions also. For example, in Helsinki, we are manufacturing big machines. Then in Finland, we have in Vaasa, where we are manufacturing a little bit this low voltage IC machines. Then we have a factory in India, we have factory in China, we have factory in Estonia, in Poland. I think we have factory in USA, in many places. So different factory in different local market to cater the local market and so on.
Okay. interesting. Thank you.
Okay, I have small question. When you talk about the electrical machine design, you have discussed a lot about the efficiency. But one important point, I think, from industry that the reliability, how you really take off that in between efficiency and reliability in your design objective. That's my first question. And the second question is that about the manufacturing errors. You know, we in our group we work a lot on the fault diagnosis. So anytime we buy the electrical machine from ABB, we buy at least 3 identical machine to create single faults, multiple faults in the machine. But 2 years ago, we bought 4 ABB permanent magnet machine. But when we open the rotor, we try to create the demagnetization fault on the rotor, one pole of the rotor. But we already found they already misalignments when you install the permanent magnet on the surface of the rotor. They already misaligned between 2 positions. So from the machine itself, when it produced from manufacturer, they already had errors. And how you would really take that into account in the design problem? Let's say objective function.
They're like very good question. I don't know if I have a good answer. Maybe the last part is this, that this kind of misalignment in the manufacturing, we cannot control that from the design. I mean, we can only provide the design, but then it is some factory guy who is doing that. And like one person said, that also sometimes come from partners also. And then coming about the reliability, that is one thing, of course, we can a little bit control from the as much from the design aspect. For example, there are a lot of applications, for example, where we need to tell that what will be the noises at certain operating point. So we can then use this kind of system level simulations to model and tell that, okay, if the machine is operated in this way and if it is designed in this way, the noises will be less. That is one thing definitely we can influence the reliability based on the customer requirement, that how much vibration and noise limitations can be there for a machine. Sometimes you have to over dimension the machines, for example. Just giving you an example to basically mitigate that noise or maybe get that energy efficiency that the customer has required. That kind of different reliability for different reliability is a very generic words of what it means for different customers and requirements from them. That you can of course influence through simulations, that you can at least attempt a better design. But then how it is implemented, like that's the reason that I said in the presentations that FAME is a comparative tool, not a quantitative tool. So with FAME, you can only expect what will be the comparative behavior. But then in the reality, there are so many uncertainties. Even with the iron steel sheet, if the punching is wrong, or if some guy has a very bad day, and then he's doing this shaft assembly, then there will be some imbalances. And it can happen so many different ways. Things can go little bit, let's say, bad, which is not the ideal situations that you cannot control, of course.
I may, from my point of view, I may have some element. I think that after the designer, when you send the design or the drawings to the factory in order for the manufacturing, we also need to specify the test, which is called approval test procedure, to verify if there could be some potential errors. So the hard part is to list on the errors and faults you have in mind, and to specify the corresponding tests in order to, well, for the manufacturer to test and to say is it how to say conform or not conform.
I think majority of the time, if you are making a very big machine, they go for this kind of a factory acceptance test. So it goes for a test.
Yeah.
And when you have a series productions, like I think what Khang was mentioning, that they
Yes.
have this kind of a small motor. They are
Small
like a series,
motor.
small motors. They are series production, so you cannot do individual testing. So you have to just really believe in the process. And of course, that's how you have Six Sigma processes in the automations, that you keep on iterating to make the process neat and clean and like that. So that is the difference in research and industries, is that, like I said also in the presentation, that implementation is the key more than the innovation sometimes. So how neatly you can do the productions, how good your production cycle, factory settings, all those small things, they influence.
Yeah, so it always depends on the how to say, the project and the size. If it's a prototype, and it can be simplified. And if it's in serial production, so it should be like more strict. Well, but yes, I see. Thank you
Good
for
point. Good point.
presentation.
I had a last question then. I know ABB, you had your own software, finite element software, actually developed from Arrakio, from AppSysMac, isn't it?
Yes.
And then, but you not only 2D, so that's why the reason why you use the commercial software not due to 3D. Is that correct?
Yes.
Yeah, but I think there are some researcher and some person from companies in this meeting. Would you advise the new company or big company should invest on developing their own finite element code for their product, or they should use commercial software?
Is this question for me? Okay. I would say that ABB has that kind of a open source software also. I mean, ABB was a part of this big Elmar project. So where we have developed the 3D software with Elmar, and we had so Elmar was this kind of, I hope many of you probably know Elmar. So it's like a open source 3D electromagnetic software. But the thing is this, that with ABB is a very big company, and it has so many different machines and so many different designs. So reliability is another question. And what we have found is this, that with open source software, that reliability quotient is very bad. Then, for example, with Maxwell, for example, we have that done. That's why this kind of integration, that we have a very reliable simulation results coming up. And as you have seen that we have integrated it so well with our software that a designer does not need to spend 1 week to make a machine. I mean, it is like a one click and the whole 3D design will be created for that machine. So then it is very fast also for us. So reliable and fast, and that's why. So I would say that I will not suggest any company to reinvent the wheel, because it's really not worth it to make it for one company to have their own 3D software. It takes a really lot of time, but that also depends upon the resources. If you have a very good resource who can do that, and there is no other project, only that, then if you can allocate money and budget, of course it's possible. But I think that that's always a compromise and that kind of thing, like resource, budget, and that kind of thing.
Thank you very much. I think we should move to the next presenter, and then
Thank
we
you.
will have more discussion at the end. Okay, the
Thank
next
you.
presenter. Thank you very much, Victor. We will talk later. I think probably at the end.
Thank
of the
you,
meeting.
Victor.
Okay. Thank you, Victor.
Talk to you later.
I think
Thank you, Victor.
the next